Let us see number system of grade 9 CBSE. Book referred is NCERT book. After this session, you will be able to define number system and able to differentiate between the rational numbers and irrational numbers and able to solve exercise problems. As per the number system, it is like counting starts. Let us assume if you want to count 1, it will be keep on increasing by 1. 2. Next, upon adding the 1 to the 2, it will be 3. Next, upon adding 1 to the 3, it will be 4. Upon adding 1 to like this, it will be keep on continuing. Let us see what are the different types of numbers system we do have. This is, let's recall the natural numbers. Natural numbers are the set of positive integers that are commonly used for the counting. 1 apple is there, 2 apples is there, 3 apples are there. In this ordering, so it will denote this one as n. Whole numbers. Whole number set of non-negative integers that include all natural numbers and 0. It is denoted with this w. Integers are set of both whole numbers as well as this negative integers. So here negative numbers -3, -2, -1, 0, 1, 2. The set of integers are represented with this z here. Rational numbers are the numbers which are expressed as a quotient of two integers, where the numerator is an integer and the denominator is a non-zero integers. If we will be having the denominator as 0, we will get this number is not different. That's why for the rational numbers, denominator should be non-zero. It is represented by p by q, where p and q are integers except the q should not be 0. Equivalent rational numbers. When we will say equivalent rational numbers, mean when the simplest value of that fraction is equal, then we call it as they are the equivalent rational numbers. For example, we are considering this 1 by 2 and 2 by 4. We will be getting here 2 or the cancellation of this one, 2 1s are 2 2s are. So we will get the value as is both for this 1 by 2 is also 0.5 and 2 by 4 also 0.5. That's why these two are equivalent rational numbers. Let us see irrational numbers. A number is called as an irrational number if it cannot be written in the form of p by q. So as we can't express it in the form of p by q, we call it as an irrational number. Example √2, √3. When we will be using the square root of the 4, we will be getting this two values. One is a negative, this positive. Pythagoras in Greece, a famous mathematician and philosopher, were the first to discover which were the not rational around the 400 BC. Those numbers as they called as irrational numbers because they cannot be written in the form of ratio of two integers like p by q. That's why they are calling it as this irrational number. Example, √2 is an irrational number and pi is an irrational number. Real numbers. The collection of the real numbers is denoted by r. It includes both rational and irrational. Rational numbers can be expressed as a fraction of p by q, and the irrational number cannot be expressed as such fractions. And it will include the irrational numbers as a √2 pi. Each real numbers correspond to a unique value in the number line. And it conversely, every point on this line represents a unique real number. This concept is a fundamental understanding like how we will be organized this one. That's why it's like real numbers always it will be underlined. It can be any value that can represent approximately that value. For example, location of √2. We know that √2 is an irrational number, but how we will able to locate at a number line, let us see. When we are drawing here, OA will draw the 1 unit. And this OC is a 1. This is a square, right? If it is in the form of square, like we want to find the diagonal, OB, the value of OB is equal to square root of OA square plus AB square. This implies square root of 1 plus 1 is a √2. Now with this O as a center, radius is a OB. Let us draw an arc. It will intersect at point P. except at point P. That's why the length, if you measure OP, will get as is 1.4 approximately. So the OP value is represented as a root 2 value. So this is, although we are considering this as a irrational number, but still we can represent it at a number line. That's the concept of the here how we are going to look at. Similarly, we can locate root 3, root 5, all the irrational numbers on the number line. For example, now how we will convert the real numbers in this decimal expansion. See, the real numbers can be this like terminating decimal number, non-terminating, non-recurring, like this. For example, 10 by 3. So this is non-terminating. How we will be doing? 3 3 is 9. We will be getting again remainder as a 1. Next again we will be taking this 0. Then 3 3 is 9. Again we will be getting this 1 as a remainder here. Then 3 3 is 9. 1 again we will be getting this. So if we keep on doing, it will be non-terminating. It will not at all terminate at all. So we will be keep on getting the remainders as a 1. Now let us see 7 by 8. Here when we are multiplying 8 with the 7, 8 8 is 64. Next we will be getting this 8 7 is 56. Value will be this 40, 8 5 is. If we understand this one here, we will get the remainder as a 0. So the difference between first and second one is, the first one we are not getting the remainder as a 0. How many steps we will be going? The second one will be getting the 0. So that's why this is called as a terminating decimal. Now let us see 1 by 7. 1 by 7 also it will be like 7 ones are like it will be keep on going. Let us see for the statistics for the 6 digits. So we will be 7 4 is 28, we will be getting 7 2 is we will be getting this value. If we observe the remainders and the divisor, finally see it will be keep on repeating. 7 7 is like it will be going 49, but then again the remainder is 1. Again it's continuing from this step. Again it will be all these steps will be keep on repeating. So when we will be again it will be coming, we will get the value as a again 142,857. Similarly again after this 142,857. So this will be keep on coming 0.142,857, 142,857. That is the value of this 1 by 7. So it will be remainders will be keep on 3, 2, 6, 4 like that, and this divisor is 7. So now as we have seen in this previous, we know that when the remainder becomes a 0, that we call it as a terminating decimal. When the remainder is not becomes a 0, that we call it as a non-terminating decimal. Examples for the terminating decimals are 1 by 2, 7 by 8. This is there are many examples. Examples for this non-terminating are 10 by 3, 1 by 7. In this previous example you have seen 10 by 3 is a 3.33, 1 by 7 is a 0.8571, what like this we keep on coming. Next, operation in the real numbers. We know that generally multiplication will be doing it. When is addition and subtraction of the operation done on the rational and irrational number, the resultant will be irrational number. For example, 2 is a rational number and root 3 is an irrational number. Okay. See, when we are adding a rational number to this irrational number, this 2 plus root 3 is an irrational number. When we are multiplying or dividing operation done is the rational numbers with an irrational number, the resultant number is irrational number. For example, here a rational number is assumed as 3 and this irrational number is a root 3. 3 by root 3 is obviously the result is root 3. So when we are dividing, this one is this root 3. Similarly, 2 we are multiplying with this root 3. When we are multiplying with this value is 2 root 3 we are getting. When two irrational numbers are added or subtracted, it may result to rational or irrational based on some conditions. For example, root 3 minus root 3 is like the two irrational numbers subtracted, multiplied. So 2 root 3 into root 3, that the 2 here. This is root 3 into root 3. So this both are irrational numbers, but we are going to get the value as a rational number. It sometimes based on the condition. When we are multiplying root 3 into root 2, although both are irrational numbers, still we are getting the irrational number. But in the case 1, As both are irrational numbers, still we are getting this rational numbers. It depends on the condition. That's why it may result either rational or irrational. These are the few positive real numbers like a and b if we are taking. Then root ab is equal to, we can multiply the root a into root b. Root a by b is equal to root a divided by root b. Root a plus root b into is equal to root a minus root b. It's nothing but a minus b. So root a plus root b into a plus root b into a minus root b is equal to a square minus b. Root a plus root b into root c plus root d is equal to root of first number in a into c, root of ac, next a into d, root of ad, next b into c, root of bc. Similar at the end, b into d, root of bd. Root a plus root b whole square is the formula we will apply x plus y whole square. It's nothing but x square plus 2xy plus y square. Similarly here root a root b, in place of x we will be substituting as a root a. So root a whole square is a square, 2 into root ab, root b whole square is b. Loss of exponents. When we will be exponenting this one, if the base is same, when we are multiplying with this, then directly we can add this exponent. So it implies a power m into a power n is equal to a power m plus n. When we are using the power of the second exponent, we can multiply the power directly. For example, 2 square whole cube is nothing but we can make it as a 2 power 6. Like simply a power mn is equal to a power m into n. When we are dividing this exponents with this one, value of this we can subtract this. So a power m divided by a power n is equal to a power m minus n, where m is greater than n. If n is greater than m, then it will become a power minus m plus. If base is different and exponent is same, directly we can multiply the base value. That indicates a power m into b power m is equal to ab whole power m. Thank you. We'll see you in this next chapter, exercise value. Thank you.